Talking about stars and bars. Stars and bars is a nice graphical tool to solve distribution problems. It pairs really well with the skill of overcounting. Let's get started with a simple example. Say we have 3 kids and we want to distribute 8 candies to them. There are many different ways which we can try to figure out how many ways to distribute the candies are. One thing we can try is just testing out all the cases, but a smarter way is just to draw it out. Let's say each of these dots are the candies. So I'm going to draw out 8 candies. So as you can see, 8 candies are drawn. Then I'm just going to assume that each kid gets whatever region they get. For example, if I draw this, you're going to see that kid 1 gets 2 candies, kid 2 gets 3 candies, and kid 3 also gets 3 candies. You can also have a configuration where a kid gets no candies, where there's nothing between the 2 bars. So you have 4 candies for that kid, then 0 for the middle kid, and 4 for the other kid. In general, for n regions, or like get people to distribute, there's always going to be n-1 dividers. So now, the total number of ways which we can distribute the candies to the kids is just a permutation of the original setup. So there are 10 objects in total, so there are 10 factorial ways to arrange them, and we have to divide by 8 factorial to account for the overcounting within the candies, so 8 factorial, and then 2 factorial for overcounting within the bars. This will get us an answer of 45 in this case. Another very useful thing in stars and bars is the idea of reservation. Let's say in the previous example, the middle kid became very upset because they couldn't get any candies. So now we're going to say that each kid must get at least 1 candy. So as you can see over here, I have another setup of 8 candies, where if I just reserve 1 candy for each of the kids, like this is kid 1's, this is kid 2's, this is 3 kids, then the remaining candies I can just distribute. So like if I just draw out a 1, 2, 3 tally mark chart of how much candies they get, they're all starting at 1 candy, which is very good for the purpose. So they all have 1 candy, and then the set of 5 candies can be distributed anyway with no restrictions like we did in the previously. Like for example, if we get 0, 2, 3 as our split, then everyone will still have above 1 candy, as in the worst case of getting a 0, nothing's just added. This can even be taken generally, where many candies can be reserved for different kids, and you can customize it. Like let's say in our 8 candies I have presented here, one kid wants 2 candies and the other kid wants 3 candies. So I'll reserve some candies for the first kid, I'll reserve some candies for the second kid. And then I just have this as my new distribution set. So reservation gives us a very great idea of what the lower bound would be. Now let's think about stars and bars in a more general equation form through another example, like a equation setup. So let's say I have the regions x1 plus x2 all the way, so dot dot dot, to xn is equal to some value r, where each of xi is like an amount which the region gets. So now let's think about how we can solve this using the information we learned in the past. We learned that r can be the total because all the regions are adding up, so this is just the total. So for this information, I'm just going to draw out r dots. So here we go. So this is r dots. Now, since we know that there are n regions, there are n-1 bars, so I'm just going to draw out n-1. So this is over here. Now, we can use the idea we used in the past. There are r plus n-1 total ways to permute, divided by r factorial ways for the stars or the dots, and then n-1 ways for the bars. Since we know that the choose expression n choose k is equal to n factorial over k factorial times n minus k factorial, we can think of this as a binomial, where n in this case is just r plus n-1, and then k in this case is just r. So this is our general form of stars and bars for non-negative. I encourage you to pause the video as an exercise and try to show a form if it's positive. So try this exercise on your own. Now we're going to move on to our example, which puts together all the skills we have learned. I'll give you guys a few seconds to read the example, pause the video. So now let's go over the example. So as we can see, there are 16 shares which are being presented. So I'm just going to draw that out really quickly. And the conditions are that each person must get a positive amount of shares. So like no one can get 0. So we can immediately start with using reservation. Like just taking condition 1 into account, we can just reserve for 4 stocks for each of the different people. So using our stars and bars, we have 12 to distribute, and since 4 people, 3 dividers, we're going to have this right now. So we have 15 choose 3 with only condition 1. Now our second condition is that we have no person can have more shares than all 3 people combined. So we know that if a person has 9 shares, then there are only 7 shares left for the other people to share. And 9 is greater than 7, so this is not allowed. So we have to subtract off all these bad cases from the total with only condition 1. So like I'm just going to remove these reservations for now. So let's say I reserve 9 candies for someone. So this, without loss of generality, will be for person 1. Now we have 7 candies left to distribute. What's nice about this is that we cover all the cases from one person having 9 candies to one person having 16 candies with themselves. So this all has to be subtracted out. And since we have to keep following our condition, since right now we have 9, 0, 0, 0 as our setup, everyone has to have a positive integer amount. So 9, 1, 1, 1 will be what we're trying to do. So if all of these 9 candies are reserved for person 1, then I'm going to reserve 1 candy for person 2, 1 candy for person 3, and 1 candy for person 4. So I have 4 candies to distribute among 4 people. Since like after all the reservations are done to not break any conditions, this is what we have left. So now let's solve out the problem. So 4 plus 3, because n minus 1, choose 3 barriers is equal to 7 choose 3. So should the answer just be 15 choose 3 minus 7 choose 3, because we have all of it with condition 1 and we're just subtracting off condition 2. Actually, it's not the case. I recommend you pause the video and try to figure out why. The reason why this isn't covering everyone is that this is only if 1 is the person with the most stocks. But what if person 2, person 3, person 4 also won't have the most stocks? They're very symmetrical, so we have to subtract off more to account for this. So since there are 4 people who could be in this position, we have to multiply this amount by 4. So now, this is a pretty easy computation to do, so I'm just going to save us some time and give the answer as 315 as the result of this computation. Thank you for listening, and I hope you learned something new about stars and bars.